we might be going back to school one day, but we might also not. I don't know. So I actually hoped Ivan would be here. Is that something I talked about? We'll just check him off the list. I have a couple things I want to show you about my Frisbee toss because it's super cool and awesome. And then I have a little physics lesson to give you as well. It's related to this thing. Remember, my battery died the other day, and I remembered something about physics. I'm going to teach you a little bit of physics lesson. And then we'll get into vectors for today. Oh, actually, before that, we'll take a look at some of the homework. But first, this is mostly about me. So this is, let's be clear. I want to show you my world. So here I have for you, I'm going to play for you 2 short videos that, actually, no, let me show you the pictures first. The pictures first. So this weekend, my son Matt and his wife came over and visited us, which was really fun. And we went out Saturday night. And I don't know if you remember Saturday night, but it was pretty windy. It was kind of windy all weekend, but Saturday there was a whole lot of wind blowing. So this is actually Matt's throw. He actually crushed it. He put this X-Xylo literally on the tennis court. And for a little bit of cool photographic perspective, that's it sitting on the court, right? Isn't that great? And up here is where we threw it from, which is 100 yards away. So he killed it. I was not able to get that far in the wind. So I was a little discouraged, a little frustrated. We're like, we're going to try it again on Sunday morning. So that's the X-Xylo. And then he actually did some looking. I guess people have actually thrown this thing over 200 yards. There's videos online. You can go look at it. They throw it 200 yards. This was 100 yards. Great. All right. But again, this is about me and how great I am. So I'm going to play for you the first of 2 videos, and you will get to see one of the coolest aerobie throws ever. The problem is, I will tell you, that Matt lost the Frisbee in the camera, and so you don't get to see where it lands, but I will show you where it lands. I have a video of that in a second. All right, here we go. Go, baby, go, baby. Oh, my God. I'm done. Okay, so where did that end up? I will show you where that ended up. Here again is an overhead map of where we were at. My house is over
welcome
here.
to our first official field trip of Precalculus.
What is that?
Kind of glad to be done with.
I don't want to do this. No. So we threw it from this spot right here, and the tennis court obviously is right there. That's 100 yards right there. I put my Frisbee, let it be shown, right here. There's a little power box right here. Even with the pool here, I put it right in this little indentation. So I'm going to show you what it looked like from the other end. This is the backside of it.
So here's the resting spot, and yeah, I kind of crushed it. Pool, tennis court, and about 160 yards away where I threw it from. Trig, ladies and gentlemen.
So, you can all be quite impressed that your teacher has got mad skills with the aerobie. 160 yards, I paced it off. It was a win all around. Thank you, I appreciate that. I appreciate, let it be known that this old man still got some left in his wings. So, okay, so to answer the question, and here's the thing I got, of course, started thinking about is our calculation was 150 yards from my house to the tennis court. So I don't know if I have the guts to try it again, but anyway. Law of signs worked, we calculated, everything worked out, everybody's happy. We can move on, yes? Okay, oh, Ivan, you're here. Ivan, I have a message for you. Are you here?
Yes.
Yeah, hey, you gotta get a hold of Mr. Hall.
Why?
Because you're the salutatorian and you got to give a speech at graduation.
And he tells me this now?
Well, he's been trying to get a hold of you.
He has my email.
We had a meeting with all the seniors yesterday. Remember how great that meeting was? Foster and Ivan, how great that meeting was? Yeah, it was fantastic. All the seniors were there except the ones that weren't.
Oh, darn.
Anyway, he's trying to get a hold of you because you have to write a speech.
All right.
So would you email him or contact him quickly and
Yeah.
let him know that
Yeah.
you're alive?
Got
Okay.
Thanks for letting me know.
Sure, no problem. All right, so back to other things now. Let me turn off the sharing so I can show you the video. Okay, so this is my stylus pen. And remember, it died last week and I got to charge back up again. I want to show you what's inside. And I don't know if you guys, any of you know this, but this is a comprehensive course here. It's not just about math. This is a little tiny battery. You ever seen a battery like this? You know about double A's and triple A's, right? C's and D's and 9 volts. You know what this size is?
Quadruple A.
It's a quadruple A, right? Right, so some of you have seen this before. So it's a quadruple A battery. And, you know, if you've done any looking at batteries, you may have noticed that they all, with one exception, come in 1.5 volt voltages. So whether it's a double A, triple A, C, or D, those big ones, they're all 1.5 volts, except for, obviously, this one, which is a 9 volt. So I'm sitting there thinking, all right, what am I going to do if my stylus dies again? Because where do you go buy a 4A battery? And the answer is they're not easy to find. You can go, go to Amazon. Of course, you can't get those very quickly. You can order them through a Walmart, but it's another supplier and it takes a long time. And they're fairly expensive and usually get a pack of like 10 or 15 of them. I don't need a 10 or 15, I just need one. So I'm trying to think, what am I going to do if this dies? Now, this is actually, my laptop is a touchscreen, so I can actually write on this if I want to, just with my finger if I had to. But then I remembered something that I discovered when I was teaching AP Physics many years ago. And we were doing a unit on electricity and batteries. And we know that, there's the reason why batteries produce charge is there's a chemical reaction inside with acids and some like zinc and some other different type of chemicals that separate the charge, put all the positive charges on one end, negative charges on the other. So we got to thinking like how do they make a 9 volt battery? 9 volts is a lot of voltage. Your car batteries is typically 12 volts. And we know car batteries can actually do some pretty serious stuff. So a 9 volt battery is actually a lot of voltage compared to the little tiny, double A or triple A. So one day I'm like, I'm just going to take this one apart. So I started taking it apart to figure out what does a 9 volt battery look like inside? What does the reaction look like? Let me know what I found. Do you know the answer to this one? Oh, okay, watch this. Take the 9 volt battery apart, and what lives inside of this? But 6 4A batteries. That's all a 9 volt battery is 6 little baby 1.5 volt batteries piggybacked together. And so each one of these represents a single battery that would go into my stylus pen. So instead of going out and buying 10 or 20 of those batteries for way more money than I wanted to, I just cannibalized a 9 volt battery and I just got 6 4A batteries all to myself. So remember that next time any one of your batteries dies. And by the way, any device like this that uses 4 AAAs, you could actually make it work with 4 4As. They just won't last as long. Why? Because the batteries aren't as big and they don't fit as nicely into those little slots. But anyway, there's 6 free 4A batteries for you right there. And I now keep this handy. So if and when my stylus dies again, I go to work. Okay, that ends the physics lesson for today. How about, let's just get better and better, isn't it? How about we do a quick check on law of cosines? Any issues? Assignments, book assignment, worksheet, problems we need to work through? Lucas says it's tedious, but doable. Is that a fair assessment? Okay. All right, hearing no complaints, we'll just go ahead and get right to this. So you might recall that this unit was called Additional Topics in Trig. So it's just sort of a bunch of scattered different ideas all thrown together. And we're moving into essentially phase 2 of these additional topics. And the topic for phase 2 will be vectors. So I'm sort of joking here, but we're almost back to a physics lesson again, because this is really tricky for me, because vectors are in many ways the language of how we talk about most of the stuff that we do in physics. And I can't assume that you all have this background in physics or with vectors. So it's a little tricky for me because I'm trying to keep it limited to a mathematical perspective, but this is really one of the major tools you use when you move on to a physics course to describe, in particular, how much and in what way things move. So this is where trig becomes a tool for moving on to other things. To get you started in this one, I want to show you a game that is probably something you all know how to play. Some of you are probably a little bit better at than others, but the game is chess. And I'm not trying to... Okay, that's annoying. Okay, I'm not trying to teach you how to play chess, but there's a couple of moves in chess that I think are really interesting and useful. Okay, so I'm going to go ahead and show you this. And the two moves I want to really focus on are how the knight moves. That was a song back in the 80s. And how the bishop moves. Okay, so I'm going to actually move this guy up here and this guy up here, and then we'll take a look at the knight and the bishop. So one thing I want you to know about chess, if you know the rules or not, doesn't matter, is that the knight can only move in one particular way. Anybody know what that is?
In L shape, 2 forward and 1 to the side.
Surely somebody knows how a knight moves. Aiden, how?
How does a knight move?
Didn't hear you. Oh, I'm muted now. Hang on. Oh, no, I'm going to be muted. I'm not going to hear anybody. Wait. I got it. I'll turn you back on. Hang on. Try it again.
2 forward and 1 to the side.
Right, and I love that, the way you describe that, because it is kind of a 2 and kind of a 1, but keep in mind, there's lots of different 2s and 1s the knight can do. For example, the knight can move up to left 1, okay? But the knight could move up to right 1. And it could actually move right 2, up 1, or potentially up 1 and right 2. So there are a lot of different possible moves. I don't want to do that. Shoot. I'm moving back over here. There's a lot of possible moves for a knight that involve 2 in one direction and 1 in another direction. So I want you to sort of think about this. What would that look like if we translated that into motion on a coordinate plane? So let's go back to this world now. And what would it look like if we went up to right 1? And let's say we started right at the origin. So if we started here, we go up to right 1, wouldn't that take us to the point 1, 2? Even though I'm going vertically first, the end result is I'm 1 over to the right and 2 up from where I was. So what we can do is we can describe that motion as a vector. That even though I can move diagonally, the end result is that I moved not to the point 1, 2, but in a manner that represents 1 unit horizontally positive and 2 units vertically positive. So now this brings up a question of what does it look like if we moved instead, let's say 2 over and 1 up? What would that look like in terms of this new notation I'm giving you like that?
2, 1.
Good. 2, 1. Exactly right. And I want to make this really clear now. Let's say I'm sitting here. My knight is at this spot, which is at the point 2, 1. Where could he go from there? Well, my knight could do a lot of different things. He could go 1, 2. He could go 2, 1. He could go up to left 1, which would be -1, 2. He could go -2, 1. My point is, from this location right here, he can go lots of different places. And these expressions here of this vector indicate motion horizontally and motion vertically without any regard to actual points on the graph. I want to make this really clear. Vectors do not have anything to do with specific points on the graph. If I go back here to my knight here, maybe I'll move him up here. If I want to move him from here, see all the dots I can move him to? Any one of those dots represents a new point he could move to, but it has no bearing from a vector perspective of what he's at, like C3 right now. We go to B5, all those different notations don't mean anything. All we're talking about is over 1, up 2, back 1, up 2, back 2, up 1, and so on. So the vector notation for the movement of the knight tells us what he can do, and it tells it in what's called component form. So component form is written x comma y, and it's written with these funky brackets. They're not less than or greater than, but that's what they kind of look like. They look in this bracket notation because they tell us, I don't care where you are in the world, from that point to the next point you're going, these are the rules that you follow. Okay? So component form will take a move that looks kind of like this and can turn it into its 2 components. And now your task from a trig perspective is to start thinking about how you would get from this kind of concept of an arrow drawn at an angle to component form. Okay, just be pondering that. The next thing I want to show you is how the bishop moves. Who knows how bishops move? Use your words, Lucas, if you would.
Diagonally.
Only diagonally, right? So
Or
let me move this guy up right here. Now, if the bishop were to move, do you see all the little dots on the screen where the bishop could move to? Why are you making faces here? You like my bishop? Okay, you like my bishop. My bishop could move either one of these diagonal spots or any one of these diagonal spots. Let's say he's going to move out here. Okay, now I want you to look here. From C1, he's moving 1, 2, 3, 4, 5, 6 spaces. But what I want to challenge you with is, did he really move 6 spaces? Because what I think he's done here is I think he's moved, and you can correct me if I'm wrong, 6 spaces right and 6 spaces up. Let me go back and show you this. From here, I'll move back here. From here, he's actually moved 1, 2, oh, sorry, it's 5, isn't it? 1, 2, 3, 4, 5 to the right. 1, 2, 3, 4, 5 up. So I don't think he's moved. Let me change this so I get these numbers right. I miscounted. I apologize. I think he's moved 5 to the right and 5 over, which means he's done this. Oops. 5 and 5. So you guys, in all of your grandeur, can you tell me how far he actually moved? You can use your
Slightly.
geometry language if you want. What's that?
Slightly more than 5.
Yeah, how much slightly more?
6.
Close. Who remembers geometry?
A squared, b squared, c squared.
Yes, but also 45, 45, 90 right triangle. The hypotenuse is 5 root 2. Ring a bell? I know some of you didn't have a great geometry experience, so I don't mean to relive that. But it's 5 root 2. And in fact, we know it's a 45-degree angle. So this type of vector, and you'll notice that the arrow has been drawn from my starting point to my ending point, indicating the direction I traveled here. This vector has what we call a magnitude and a direction. So let me marry a couple words together, worlds together now. In physics, we rarely use component notation. We almost always use, it's called polar notation, but it's magnitude and direction. How far and in which direction? Because if I just say how far, I don't know if I've gone this way, this way, this way, this way. I don't know which way I'm going. So I have to indicate the direction so that everyone is clear, again, in a physics perspective, of exactly where the motion has covered. So the stuff on the right in blue is a physics way of writing about it. This stuff on the left is the mathematical way of writing about it in component form. And one of our jobs will be to convert back and forth between a component expression for a vector and say its magnitude and direction. Okay, so what I want to do is I want to show you a quick example. Give me just 1 second to pull it up on the other screen here. And I want you to have a chance to explore this yourself in hopefully a way that will make some bit of sense. So let me switch this over. You're gonna get a chance to play around with this. So here's a screen with a whole bunch of vectors on it. And very simply, what I'd like you to do is look at vector A and describe it in 2 ways. The first way I'd like you to describe it is in its component form. This has nothing to do with the fact that it starts at 6,1 or where it ends. I just want you to tell me what the component form of this vector would be, and then also what its magnitude would be. Go ahead and take a couple seconds and play around with that. I can try and make it a little bit bigger if that is helpful. You can also use the axes to scale this. Anybody got an idea for the component form for this vector?
7, 3.
I like it. So we would write it with these sort of greater than, less than symbols. I'll do it in just a second. 7, 3. What about the magnitude? That is the length of the vector. And if you're not sure where we're going, we're Pythagorean theorem right now.
Square root 58.
This is white. What's that?
Square root 58.
Yeah, and that's exactly how I'd write it. Square root 58. So let me just switch back and we'll just walk through this so everybody gets this idea. We have this vector 7, 3. The idea being that we move 7 units horizontally, 3 units up. And that means that the hypotenuse or the magnitude, so if this is vector v, we call it the magnitude of v, is the length of the hypotenuse. Square root of 7 squared plus 3 squared is the square root of 50. Okay? So this is a useful way for us to figure out magnitudes of vectors based on their components. And again, if we were in physics, we would be interested in this angle theta. For now, it's not going to be as big a deal. We're not going to get as deep into this as we possibly could. Okay, so vectors, great. What can you do with them? What can we do with vectors? First thing we can do, we can add them. I'll give you an example. Let's let vector A be vector 4, 2. If you want to think about it, you can think about 4 and 2, and this being vector A. Vector B is going to be negative 3, 5. So if you go back to a chess concept again, vector A represents the motion of one of the pieces. Illegal move in chess, I understand that, but if it is as if it moved 4 to the right and 2 up. B represents moving 3 to the left and 5 up. And so my question to you is, what is A plus B? And if your intuition tells you, don't you just add them all up? Then you're spot on. Because the act of moving 4 to the right and then eventually 1 back to the left is going to be 3 back to the left is going to be eventually, I will move 1 unit to the right. And if you thought of moving 2 up and then later 5 more up, in fact, it's 1 cell. So when we add vectors, I'm not trying to be funny here, we literally just add the vectors. Add the x components, add the y components, and you're done. But I owe you the possibility to think about that. What if you do it in opposite orders? Now remember, a vector describes a motion in a certain direction, a certain amount of motion, a certain amount of direction. So if you were thinking about like walking yourself 4 feet to the right and 2 feet up, and then 3 feet to the left and 5 more up, you would end up at a certain place relative to where you started, this right here. What if you did them in opposite order? What if you went left first and 5 up, and then went right and 2 up? What would happen? Well, I would get negative 3 plus 4 and 5 plus 2. Which means I would get 1, 7. And so what we say is that the commutative, all right, algebra time, the commutative property holds for addition of vectors. For addition, great. Awesome. What about subtraction? Now this is where it gets really tricky. Let's say I've got, I'll try to draw these, I don't even need those on there. Wait a second. I'm just going to draw these 2 vectors in here. Let me just say I have 4 and 2. And then I have negative 3 and 5. So this is negative 3, 5, and this is So what if I want to subtract these? This we're calling A, this we're calling B. Oops. And I'm curious about this concept of A minus B. And you have a couple ways to think about this one. You can think about A minus B like somehow trying to take away or undo B. But I'm telling you, the easiest way to do this is to go back to early days of Algebra 1, which has been a while for some of you. Remember Algebra 1? Those are a long time ago. Here's what we're going to do. A minus B is simply A plus the opposite of B. So what is the opposite of B? If this is B, the opposite of B is the opposite of B, which is over 3 down 5. It's literally the opposite of B. So now what I do when I want to subtract is I go 4, 2, plus the opposite of B, 3, negative 5. And by the way, 4 minus negative 3 gets us that 7 we were thinking about. And then 2 minus 5 is minus 3. Adding vectors is just like adding everything else. Subtracting vectors requires us to add the opposite of the vector. And I will tell you that subtraction is not closed under the commutative property. Just like every other number we know, subtraction matters which direction you go. Addition does not. Okay? Okay, we have a little bit more to go. Are you guys hanging in there okay? This is a little bit in depth, and I don't guess that there's a lot of applications to this yet, but this is good stuff to know. Really good stuff to know for where you're going on in life and everything else. What about this problem here? Remember that A was 4, 2, and B was negative 3, 5. What about this problem here? 2A minus 5B. What do you suppose it means? I'm going to ask one of you to answer this. What do you suppose it means to multiply a vector by a number? All right, too many of you here, so I'm going to put you on the spot.
Multiply instead of the endpoints, just the straight distance, not the.
Talk to me some more. You're really close, I think.
You're just multiplying the hypotenuse and not
Interesting.
edge parts.
I would say that yes, you're multiplying the hypotenuse, but if I have a vector that looks like this, right, that goes over 4 and up 2, and I want to multiply that by 2, it's going to get me that, this new vector here. To do that, I think I'm going to have to multiply this by 2 and that by 2 as well. So I think it turns out that to accomplish the multiplying the hypotenuse by 2, this is actually going to be 8, 4 minus I'm literally multiplying all the components by that same factor. Yep. And now if you think about it, you can actually tackle this mathematically. Because if I were trying to change this, I'll turn it back in a second. If I try to turn this into plus and then change all those signs, isn't that the same thing I would get if I just thought about this as 8 plus 15 and 4 minus 25? Meaning, from a mathematical standpoint, you don't have to create this, what is opposite B, and then do your addition from there. You can simply effectively kind of distribute a -1 through that expression, and I'll show you in about 30 seconds even more what that looks like. I can distribute this subtraction sign and turn that into a plus 15. So I get an answer of 23 minus 20. So here's the good news. A lot of the work you're going to be doing tonight and tomorrow is just playing around with manipulating these vectors, manipulating numbers, maybe a little bit of hypotenuse and Pythagorean theorem, but that's about it. So for your reference, I want you to look at page, and you don't have to do this right now, page 419, which has a little box on it that will tell you all the different things we can do with vectors. And I'm not going to even go into it right now, but you can take a look at it and use that as a reference. Okay? All right, I have one more concept to show you, and then a quick application problem, and that will be that. Are we good for a while? I'll take that as a yes. Okay, so as you get farther into the world of vectors, and this is probably more from a physics perspective, but certainly in mathematics you see it as well, you will encounter something called a unit vector. This by itself is not something you need to worry about, but where it leads to is. A unit vector is a vector that is 1 unit long. And I'm not trying to be silly here, but you might remember the unit circle was called a unit circle because its radius was 1 unit. So everywhere you went around the circle, you were dealing with a hypotenuse or a radius of 1 unit. So now we have a unit vector that's 1 unit long, and of particular interest to us will be unit vectors in the x and y direction. So in the x direction, we call the unit vector I, and I know it sucks. One of the worst possible letters that they could use to represent motion in the x direction. That's not the imaginary number I. That's just an indicator that we're moving in the x direction. And in the y direction, we use the unit vector j. So what we can start to do is express other vectors in terms of I and j. By the way, I is the vector 1, 0. J is the vector 0, 1. I think you can appreciate that we don't need any of the other ones because if I want to go the other direction, like left, I would just use negative I and then negative j for the y direction. But what it means is that I can take a vector like this, 3, 2, and I can write it as 3i plus 2j. Okay? So where that leads us is that we can now use this notation to make our work with vectors even easier. Let me give you a quick example. I have a problem here. We're going to let u, vector u, is going to be this 3i plus 2j I just showed you. And vector v is going to be 5i minus j. So this is just a different notation for stuff that we've already talked about doing. But I want to know what 2u minus 3v is now going to equal. Well, if we write it in this form, this becomes pretty simple. This is 2 times 3i plus 2j minus 3 times 5i minus j. And now this actually starts to look just like an algebra problem. 6i plus 4j minus 15i plus 3j, and we get minus 9i plus 7j, or minus 9, 7. So I don't want you to be like, oh my gosh, this is so crazy and wild. What is he doing? I can't keep up with this. This is really just basic concepts of algebra applied to a trigonometry concept. And again, that trigonometry concept is going to lead eventually to physics applications. So you get a chance to, you can look in your book at this. There's a couple of problems that ask you to work with unit vector notation. You can think of it X's and Y's if you won't, but you will see I's and J's as you go further in math and science to help you through this process. Okay, I got one application problem for you, and then I'm going to turn you loose. Any questions so far? Okay. Here is your application problem. And this is, frankly, this is where the real value and interest, in my mind, come for using vectors. So what we have is we're going to pretend, remember back when we used to get on airplanes and fly places? Wasn't that great? Way back like a month ago when we could actually leave our house. It was great, trust me. If you don't remember, it was great. So I'm going to pretend that I'm flying in an airplane at 150 miles per hour. That's not really a jet plane, that's just, a smaller plane. And I'm doing so at an angle 50 degrees north of east. So this is a different kind of notation that you probably are not used to me talking about. But I want you to believe, I want you to believe that this is a thing. North, south, east, west. Now I know there are bearing issues that our book has gotten into with navigation on the seas and so on. I'm just saying that, look, I'm not flying due north, I'm flying a little bit farther. I'm 50 degrees north of east or 40 degrees east of north, whatever you want. I'm flying towards the northeast, but not perfectly. Maybe from our area, it'd be like flying to, I don't know, the middle of Canada. But while I'm doing that, there's also a wind blowing. And the wind is blowing to the east at 50 miles per hour. And so the question becomes, how fast am I really traveling? Am I traveling 150 miles an hour? No. Am I traveling 200 miles an hour? No. I'm traveling somewhere in between there, which is this. Now, with all due respect, we could probably do this with the law of cosines. But we're going to try to tackle this from a different perspective. What I want to do is figure out the component notation of our green vector. Green vector we'll call P for plane. We'll call it P. And then we'll call the red vector W for the wind. Question? Okay. Let's do the easy part first. How can we write W as a vector? And I'll let you use component notation or unit vector notation as you want. How do we write W as a vector? Anyone? This should be the easy one. It should just be 50 and 0. Okay? Just W. So I can write that as 50I and 0J. Now, the problem is, what do we do with P? P is a little bit more problematic because P has a, let me make this kind of funky here. P has a component that goes in the X direction, and P has a component that goes in the Y direction. You see that? We're going to break up again into genders. Gentlemen, would you please find the X component? Because isn't that X chromosome? Y, I think X is biology folks. Isn't X, whatever. Guys, you doing X's. I don't want to get weird here. I want you to find the X component of this, and all the ladies in the room, of which there are one, I would like you to find the Y component. Now, I want to remind you that what we're talking about here is a triangle that looks like this and this. We have 150 here, 50 degrees here. I'm asking you to solve for X and Y. All of you know how to do this. I'd like you to do it very quickly and find that for me, please. Anna, find the X component. Guys, all the rest of you get to find the Y component. Aiden, you good? Oh, yeah. Ivan, you good?
I'm going.
If anybody's unsure, I want you to be dealing with cosine or sine to find these. Does anybody have either answer yet? Lucas.
X is 125. About.
I'm not. Did you cut one? How'd you get 125?
Is it 96.4?
Yeah, that's what I'm getting.
I agree.
I'm doing, so just if, what I'm doing is I'm doing 150 cosine 50. And then I'm going to go along with that 96.4 I. Does anybody have Y?
$114.9.
Awesome. Which is 150 sine 50. So 114.9 J. So here's what happens now. We've got the plane that's flying on its own with a certain ground speed, but the wind is kind of helping it, right? So altogether, what we end up with is this P plus W is going to be the sum of these two vectors. So I add the i's together, I get 146.4 I plus 114.9 J. And then what I do, let me jump on the next page real quick and I'll come right back. So therefore what I have is I have 4 miles per hour that direction. I also have 114.9 miles per hour that direction. And ultimately, my end result is this vector right here, which I can write as my final speed v. Okay, so I've got the notation here. 146.4 miles an hour to the east, and then 114.9 miles north. But what is the final speed? How do you find that number right there?
Pythagorean theorem.
Hello, Mrs. Williams.
Hello.
Hey. We're just doing vectors.
Looks good.
Univectors.
I saw it. I couldn't help but come in.
I know. I don't blame you.
Man, I won't bug you guys.
All right. Well, how do we find the final speed now?
Pythagorean theorem.
Exactly right. This is back to our, our beginnings, the Pythagorean theorem. So do that real quickly. Let's find out what the final speed is of the plane. Remember, the plane's flying 150 on its own, but the wind, I think, is probably giving it a little bit of a boost. The answer?
Do you want it still under the square root, or do you want us to like
Let's actually get a decimal answer. Yeah, let's get a decimal answer. This is a good application problem.
185.79 or 185?
We'll go 0.8 miles per hour. Great. So there's a couple things I want to point out here. First of all, the winds in our planet at the higher elevations tend to push west to east. Did you know that? The jet stream, which is up where a lot of planes fly, all goes from west to east. And the jet stream speed is about 200 to 300 miles an hour, sometimes a little bit faster than that. So when you are flying from west to east, you get a massive tailwind. Now, not every plane flies directly west to east. Like if you fly to Europe, you actually fly over the top of not the North Pole, but you fly over Greenland. But you're generally flying from west to east, so you get a boost. And so you actually can fly faster when you're going to the east, as opposed to when you're flying back home to the west, or New York to Seattle, we'll say, you're flying into a headwind the entire time. So if you've ever made those trips, you're like, why is it so much shorter to fly from Seattle to New York than it is New York to Seattle? Or even Seattle to Spokane and Spokane back to Seattle. The prevailing winds always push towards the east at the upper elevations. And so you're always going faster to the east, which means the flights are shorter. However, imagine if you were a pilot. Obviously, they do computers all this right now, but if you knew how fast your plane could go, and you had to get to, we'll say, Denver, Colorado, you could aim for Denver, but that wind is going to keep pushing you away from Denver. So nowadays, again, computers do all the work for you, but there was a time when the pilots had to constantly recalibrate not just their ground speed, but their direction as well, because they actually had to fly a little bit into the wind. Think Seattle down to Denver, to southeast. They have to fly a little bit into the wind, so the wind can now push you towards Denver. So these are really interesting and complicated computation problems that, again, computers all do for us now. But the computers have to know trig as well to be programmed to figure that out. Okay, that's all for today. That's a long lesson. Sorry that was so long, but I think it was kind of interesting. So here is your today's assignment. I'll put up the second one as well, but today is 425, 9 through 29 odd. 31, 37 to 43. I hope you notice I'm giving you lots of odd problems so you can check the answers in the back. 55, 57, 62, 63. If that seems like a lot, most of it's because these early ones are going to be just simple addition, subtraction. Look at the graph, find the vector notation problem. They're not going to be really involved problems. These ones towards the end are going to be more some application problems. And then tomorrow, your extra work will be a CUDA worksheet on vector operations. Okay. So you have a couple things to work on the next couple of days. If you've got questions or like number 62 you can't figure out, or even you get one of the odd answers and you can't figure those out, either drop me a note or we'll talk about it on Thursday. We will have our next class on Thursday at 11:30 in the morning. More work on vectors. And then next week we'll move on to a third topic of this assorted topics in trig. And next week will be our last week of lessons in learning.
We should have a class at like 11 at night one day.
I'm always up then. Do you want to?
I don't know. It'd be fun.
Seriously?
Yeah.
Let's do it.
Thursday night?
Yes.
Yeah.
Yeah.
Really? Oh, you know what though? Mostly can join us because she's working till 10 now.
Exactly.
And she'll be so happy.
So, are you guys really serious? You want to have class at 11 o'clock
Yeah.
Thursday night?
Let's do it.
Go 2 a.m. if you wanted.
I'll do that too.
Let's go.
Yeah.
I'll do that. Whatever you need. We'll start with 11 o'clock. Let's not go too crazy.
Too crazy?
So seriously, 11 o'clock p.m. Thursday night. You want to meet?
Yeah.
All right. I will send out maybe an email to everyone, just reminding them. Wow, I got to write this down. You guys are speaking my language though. That's probably my
To live
prime
on the
time right
edge.
there. Huh?
Like to live on the edge.
Well, if we're not wild right here. The only thing I have to tell you, and this is sort of a weird thing, but I don't know that Zoom is going to be as good a quality when it's darker out and it's just using lights. So I might not look this good at 11 o'clock, but I'll still be fresh. Don't get me wrong. I'm ready to roll at 11 o'clock. Now, Ivan will just be waking up by then, so I know he's going to be in fine form. Plus, you have a speech to work on, dude. So, all right. So I'm going to write this down so it's official. Thursday. You know what would be really fun is if we were to welcome in May by having a class at like 11:30. Maybe I'll make it go an hour, and then we can go all the way into May.
Mhm.
Whoa.
Have May Day.
Yeah.
Mayday, mayday. Speaking of planes.
All right. Thursday, April 30th, 11 o'clock. I will see you then. Bye, guys.
Bye.